Good day from Chem Help ASAP. Let's cover the essential ideas of TLC, thin layer chromatography. Performing a TLC on an experiment or isolated or purified product is an essential skill in the organic chemistry lab. Let's start with the question, what is TLC? TLC stands for thin layer chromatography. This is a form of chromatography. Chromatography always involves a mobile phase and a stationary phase. And so does TLC. We'll talk about these later. TLC is quick, it's easy, and it's very low tech. You don't need very fancy lab equipment to perform a TLC. Great, so why would anyone want to do a TLC analysis? A few questions can often be answered through TLC. One, you can sometimes determine whether a mixture, like a reaction, contains a specific compound. For example, you want to know whether a reaction contains the starting material. Is the reaction complete? Two, you can also get information on how many compounds are present in a sample. For example, once you isolate a product, you might want to see if the product is pure. Does it contain one or more compounds? Let's see how a TLC analysis is performed in lab. Alright, well let's talk about the different things that you need in order to perform thin layer chromatography. The first thing you need is a TLC plate. And so this is a box of TLC plates. TLC plates come in a variety of forms, but this is the type that we tend to use the most, especially in our teaching labs. This is a TLC plate. It has a plastic backing, so this is a shiny backing. That is not the business side of the TLC plate. This side has a coating on it, and that is a coating of silica gel. It's basically finely ground glass. I'm going to scrape it off so you can see it definitely comes off. You don't want to just, I'm totally destroying this TLC plate. You don't want to do that when you work with one, but I just want to show that it does have a coating, and you can feel that rough surface. So this is our TLC plate. This rough surface is silica gel. This is our stationary phase for the chromatography. Okay, so what else do we need? We need a developing chamber. And here is our developing chamber. I'm a big fan of just using a 250 milliliter beaker. You can put a watch glass on top. Ideally, you want something that closes up as well as possible to not allow the loss of vapors. I would argue this is completely adequate, but some people are very adamant about the fact you need to completely seal the top. So if your instructor likes a completely sealed top, make sure you do that. Notice that I do have a piece of filter paper in here, and that seems kind of odd. What the filter paper does, and we'll discuss this more later, it helps form a chamber of vapors in here, and like I say, we'll talk about that later. But normally you need something in here that will wick up and draw that solvent up so it can evaporate into your developing chamber. Okay, to do a TLC, we also need spotters, and these are tiny glass capillaries, and this is almost set up like a salt shaker. There's a little hole in the top, so if you turn this upside down and shake it a little bit, something will fall out of that hole eventually. There it goes. And I don't know if you could see that on camera, but this is a tiny capillary spotter. This is a very fine glass tube, and this will allow us to easily and precisely transfer our analyte to our TLC plate right here. We want to use this TLC plate because it's been completely mauled by that microspatula, but the spotter allows us to transfer our sample onto the surface of the TLC plate. Okay, what else do we need? Well, we need something to analyze, and I don't have that present here in the hood. We'll talk about that later, but we do need to analyze something, and we need that could be a sample of a reaction mixture. It could be a sample of a purified compound. It could be any number of things, but we'll need that, and we'll discuss that in the next clip. What else do we need? We will need a pencil. The pencil will be needed to write on our TLC plate. And you might say, nah, I don't like pencils. I'm kind of more of a felt tip marker person. Well, you really need a pencil to write on this surface. Markers will leave organic inks on the surface, and when we perform our TLC analysis, those inks and those markers will actually travel on the plate and mess things up. So a pencil is required to write on a TLC plate, and we will want to write and make notes on here just so we can keep track of our spots and have a point of reference on the plate. So you need a pencil. That's a given. We also need a way to visualize the results of our TLC analysis, and for our purposes we're going to use a UV lamp. There are other methods that can be used, but we're going to use the UV lamp. Finally, we do need a developing solvent. So I mentioned that the TLC plate has this silica gel. This is our stationary phase. We need a mobile phase, and that is our developing solvent. And I have 10 milliliters of the solvent that I want to use for this experiment right here. You might need to make up your solvent. So that isn't just a 10 milliliter sample of hexane or ethyl acetate or ethanol. That is a custom made mixture based on what we need. We'll talk about creating the developing solvent in a little bit, but what we're going to do is we're going to put that developing solvent into our developing chamber. And as it turns out, a 250 milliliter beaker is a perfect match for 10 milliliters of solvent. So 10 milliliter graduates are very handy, and you fill this thing up with the mixture you need, put it into a 250 milliliter beaker, cover it up with a watch glass with a piece of filter paper in there, and you're pretty much ready to go for your TLC analysis. So let's break here and we'll talk about some other aspects of running a TLC. Let's make up a couple samples for a TLC. So I'm a huge fan of using these. You need a small test tube for this. And I love these teeny tiny baby test tubes. You don't need a teeny tiny baby test tube. You just need some kind of test tube. But these little ones are particularly handy. Now there are two different analytes that we're going to analyze. One is 4-hydroxy acetophenone, or I'm sorry, this is 4'-chloroacetophenone. Excuse me, and this is 4'-hydroxy acetophenone. And one is a solid and one is a liquid. And TLC can analyze both solids and liquids, but we'll see how you deal with both of them. So tell you what, since I grabbed this one first, let's go with the 4'-chloroacetophenone. This is a liquid, and so I'm going to use a pipette to dip in here, and I'm just going to touch this pipette to the surface of the liquid. And we have a small amount of liquid in here. That's more than I actually need. I'm just going to stick this into the tube. I don't want to get all that. I just need a speck, just enough to see that I got a little bit of liquid in there. That's plenty. I don't know if that's clear, but there's not much in there. It's part of a drop. It's all we need. It's plenty. Like we say, this method is fast. It's simple. It's inexpensive. And part of what makes it fast and easy and inexpensive is because we don't need a whole lot of reagent. So now we can't add this pure liquid to a TLC plate. So we need to make this into a more dilute solution. So I'm going to add some solvent. This is just acetone here. You need a fairly volatile organic solvent. And I'd say in most labs that's going to be acetone, as long as your stuff doesn't react with acetone, or it could be ethyl acetate is another common solvent. That is our analyte solution for 4'-chloroacetophenone. So I'm going to put it in this little beaker. It's labeled with a CL, and now let's go to the next analyte. So here is our 4'-hydroxyacetophenone. Again, we're going to use a small test tube, and let's see if I can do this. Yikes. I'm just going to put this. Oh, that's plenty. Okay. So I stuck that in there and just got a crystal. Let me get it out of the way. Just a small crystal. It's sitting on the bottom there. You can't see it very well. That's all we need. We just need crumbs of this material. Just like we did with the liquid, we give it a little squirt of acetone. You can say, oh, but how much acetone? Just a little squirt. Don't worry about getting it exactly right. You just need to make a dilute solution. A small amount and a little bit of solvent, and that will be just fine for detection. And we're going to put this over in the beaker marked with an OH. So there are two analyte solutions, and with those solutions we can now get started on preparing and running a TLC plate. Let's now run our TLC plate. So the first thing I'm going to do, I'm going to take our developing chamber. This is my 250 milliliter beaker. And remember, it has that piece of filter paper in the back. And I'm going to add in my developing solvent. And that's 10 milliliters, in this case, 10 milliliters of 20% ethyl acetate, 80% hexane. So that's 2 milliliters of ethyl acetate and 8 milliliters of hexane. And that solution, that's going to be our mobile phase. We're just going to let that sit. So what's happening is that the solvent is evaporating, it's creating a saturated vapor chamber in here, and that's actually a good thing. That's going to help our TLC plate run better. That does, however, take a few minutes. So let's put that to the side, and now while we're letting that do its thing, we can go ahead and prep our TLC plate. So let's get out a TLC plate. There we go. Almost. Now, people try to handle these from their edges because you don't want dirt and oils from your hands getting on your TLC plate. That is possible, but just make sure your hands are pretty clean because you have to have pretty dirty hands to make a mess of your TLC plate. So here's our TLC plate. I'm going to run what's called a 3-lane TLC plate. We'll go more into details about different types of TLC plates. But for a 3-lane TLC plate, I need 3 dots toward the bottom of this plate. And so I'm just going to write these dots right in a row. You'll notice that those 3 dots are a little bit up from the bottom edge. I want to make sure they're up high enough so that when I dip this into this liquid, the liquid won't be above the spots. And I think that'll be more clear in a moment. So that's our TLC plate. Now we have our analyte solutions. Let's use those. And let's start with the 4'-hydroxyacetophenone. And I'm going to touch this spotter to the liquid in this test tube. Now, it's not always clear if we got it or not, but it'll be clear in a second. So I'm going to lift this back up. And I'm going to touch this spotter. Normally I'd have this flat, but I want you to see it a little bit better. I'm going to touch this spotter to 2 of these spots, the first 2. There's one. I don't know if you can see that get dark real fast. And there's another. Now what's happening is this solution with acetone is being, by capillary action, being drawn onto the TLC surface. And so you can see the wetting of the TLC surface. However, our solvent was acetone, which is very volatile. Pretty much as soon as it hits that surface, it evaporates away and it becomes invisible, or essentially invisible. So, but there are small amounts of our analyte in those first 2 spots. Okay, let's toss that to the side. Now let's get our spotter. Another one. Get out of there, baby. Okay, there we go. And now let's go after the 4'-chloroacetophenone. Again, a dilute solution. We tilt it. We touch it to the tip. And I'm going to hold it. This is much better done flat than holding it up. But I'm going to touch this spotter to the 2nd and 3rd dot now. So the first time we did number 1 and number 2, and now we're going to do number 2. Just a touch. And number 3. Just a small touch. Perfect. So this is now our plate. That's it. And so we just kind of wave this around a little bit, make sure that acetone has dried off of there, and it has. I mean, it happens in seconds. There's no reason to wait on it. Now that we're ready, we need to put this TLC plate into our developing chamber, and hopefully we have a nice saturated solvent vapor in there. You can use forceps to do this, but tweezers, I tend to use my index finger and thumb as tweezers. Place it in there, rest it against the back. And what we see now is the solvent in the bottom, the mobile phase, is now slowly creeping up this plate. It's because it's being absorbed onto the stationary phase. Remember, we put our stuff on the stationary phase. And so we're going to let this mobile phase creep all the way up the plate. Not quite all the way up the plate, but pretty close. So tell you what, we will, and you don't wiggle this around. You want to keep this pretty still. Just let it do its thing. in peace. So we'll come back once this TLC plate is done. How exactly does a TLC work? Here on the left is a TLC plate in a developing chamber and soaking in a mobile phase. The positions of the spots are on the plate, in pencil, of course. As the solvent wicks up the plate, the mobile phase flows past the compounds at the spot. As the mobile phase moves past the spots, each compound in the spot will have the opportunity to either stick to the silica gel surface of the stationary phase or flow up the plate with the mobile phase. In general, more polar compounds will stick to the plate. Less polar compounds will flow up the plate. Over time, the mobile phase will eventually get close to the top of the plate. The plate needs to be pulled from the developing chamber before the solvent reaches the top of the plate. Once you remove the plate, mark the position of the solvent. This is called the solvent front. You then visualize the plate to see where the spots appear. Those are those guys right there. For a 3-lane plate, any spot that appears on the left or the right should also appear in the middle lane, the co-spot lane. All right, that was a nice little break. And in the meantime, let's say this took, 5 or so minutes. The solvent has crept up the plate. And now I'd say it's about 3/4 of the way up the plate. There's no fixed amount that you have to let the solvent go up. Now, the farther you want it to go, the longer it takes. So there is a cost to letting it go farther. But you do want it to go some distance because that's going to give you easier to interpret results. Regardless, you don't want it to go all the way to the top of the plate. You want to leave it a little bit of room left. Now, once you're ready to pull the plate out, you do need your pencil ready, because as soon as you pull this out, we need to mark where that solvent went. So I'm going to pull this out, bam, open that up, and really quickly, best I can, estimate where that solvent is. It's called your solvent front. And now, because once we mark it, very quickly the solvent will evaporate off this plate, and it won't be totally obvious to us where the solvent was and wasn't. So we want to make sure we mark it immediately. Don't wait a few minutes and say, oh, I think it went about there. Just have your pencil ready and mark it. Okay, this is our plate. So now we're ready to visualize our plate once we have completed the exposure of the plate to the developing solvent with the mobile phase. The last step is visualization of the plate. On the screen is a TLC plate, the same one developed in this video. It's being visualized with a UV lamp. The TLC plate we used is coated with a UV active dye. It glows under UV light. If a molecule on the plate, that would be from one of our spots, absorbs UV light, then the plate will not glow in that particular spot. The darker spots on this plate represent the positions of compounds on the plate. Note that all the compounds, they were marked and placed initially at the bottom of the plate. We can still see the pencil marks across the bottom. The compounds on the plate that we see under the UV light, they have traveled up the plate. The left spot moved less. It's the more polar compound. The right spot moved more. It is less polar. When you have the TLC light on, it is important to mark the positions of the spots. The spots won't be visible once the light is turned off. This picture isn't very exciting, but here is the TLC plate that had its spots marked. There are a few important features. One, we can clearly see where the spots were placed on the plate. Those are the 3 dots across the bottom. 2, we have all the spots from the UV light clearly marked. I've marked the center of the spots. Some people prefer to circle the entire spot. 3, we have a line across the top that shows how far the solvent traveled up the plate. This is the solvent front. From this information, we can calculate something called the RF value of the spots. The RF value is a characteristic of the compound on the plate. The RF value of a spot is equal to the distance the spot traveled divided by the distance of the solvent front. Okay, so RF values will always have a range from 0 to 1. Furthermore, it's important to record not only the RF value, but also the composition of the mobile phase. So I've measured these spots. The solvent front, we're going to measure this from those initial dots, is 5.0 centimeters. The top spot, this one, traveled 2.3 centimeters. The lower spot only traveled 0.6 centimeters. So from these numbers, we can calculate the RF values. The bottom spot has an RF of, let's see, that's 0.12, which is 0.6 divided by 5. And the top spot has an RF of 0.46, and that's 2.3 divided by 5. The mobile phase, and it's important to record this, is 20% ethyl acetate, 80% hexane. Note that these two compounds were 4'-chloroacetophenone and 4'-hydroxyacetophenone. Turns out, I've crisscrossed these. The 4-chloro is the top spot and the 4-hydroxy is the bottom spot. So the OH of the hydroxy compound forms good hydrogen bonds with the stationary phase, the silica gel, and therefore the hydroxy compound is more polar and travels less on the plate. It sticks to the plate. Less travel results in a smaller RF value. The chloro compound is less polar, so it travels more. It gives a higher RF value. Let's see why reporting the mobile phase is important. On the slide are 3 different TLC plates. Each plate has the same compounds on it, but the mobile phase used to develop each plate is different. On the left is 10% ethyl acetate, 90% hexane. In the middle is 20% ethyl acetate, 80% hexane. And on the right is 50% ethyl acetate, 50% hexane. Ethyl acetate is more polar than hexane, so ethyl acetate gives a more polar mobile phase. Let's just look at the RF of the chloro compound. That's the dot on the right of each plate. As we increase the amount of ethyl acetate, the RF of the chloro compound goes from 0.29 to 0.46 to 0.59. So RF is not constant. It varies with the identity of the mobile phase. You must report RF values with the corresponding mobile phase. Using a UV light is great for visualizing spots of compounds that absorb UV light. But what if a compound is not UV active? Well, it won't show up in a UV lamp. Fortunately, there are dozens and maybe hundreds of different ways to visualize spots on a TLC plate. On the left of the screen is something called an iodine chamber. Those dark spots on the jar are crystals of iodine. In a sealed jar, there is a lot of iodine vapor. Iodine reacts readily with many organic molecules. When this happens on a TLC plate, it makes a dark spot. To the right is our original TLC plate that spent some time in an iodine chamber. Just like you can mark spots under a UV lamp, you can mark these dark spots from the iodine. These spots do fade over time. Note that the top spot The chloro compound does not visualize nearly as clearly in iodine as the hydroxyl compound. Different compounds sometimes require different visualization methods. There is no single universal visualization method for TLC plates. Now that we know the ins and outs of TLC, let's revisit why we would run a TLC plate in an organic chemistry lab. The first reason is to monitor a reaction with a 3-lane TLC plate. Here on the left we have a hypothetical TLC plate. At the start of a reaction, we would make a spot for the starting material, that's on the left, with a sample in the middle as well. We could also spot a sample from our chemical reaction with a spot of the reaction in the middle as well. So the left is our starting material, the right is our reaction, and the middle is called the co-spot. For a reaction that has just started, the TLC plate should look something like this. The starting material hasn't had time to react yet, so the reaction only shows the starting material. Note that you often have multiple starting materials, so you might have multiple spots. Once the reaction has been going on a while, the TLC plate might look like this. The reaction will still have a lot of starting material, but you may also have a product spot appearing very faintly. Note that any spot that appears in the reaction or starting material lanes should also appear in the middle co-spot lane. If we keep going, the reaction should look something like this. The starting material is almost gone, very faint, and the product is now a darker spot. Once the reaction is complete, the starting material should be completely absent, and it is. The only spot in the reaction is the product. So as you can see, a sequence of 3-lane TLC plates can allow one to monitor the progress of a reaction and even determine whether the reaction is complete. We can also use a TLC to check the purity of a reaction product. On the left is a single-lane TLC of a reaction mixture. This is the crude reaction. A reaction may show multiple spots. Your product, perhaps some side products, and even some leftover starting materials. From our perspective, anything beyond our product is an impurity. Isolation or workup of the product normally involves some kind of extraction, which might remove some of the impurities. The isolated product may be a little bit cleaner. Note that this spot is gone, but impurities will likely remain. After purification, which could be a recrystallization or a distillation, we should ideally see just one spot, a spot from our product. Very often, organic chemists will say that their product is one spot by TLC as a sign of purity. Note that not all impurities may show up on a TLC plate, so just seeing one spot does not conclusively mean that the product is pure. Seeing just one spot, however, is evidence of purity and always a good sign. That is a full introduction to thin layer chromatography. I hope you found it informative. Please subscribe, like, or leave a comment. Take care.